Hi everyone, welcome to the 5th episode of All Things Math. This is part 1 of a two-parter on calculus. In this video, we'll be going through basic concepts of calculus and differentiation. When we first think of calculus, what comes to our mind? What is calculus exactly? How does it work? Is it difficult? Well, calculus is not as hard as you think, and that is what we're going to be exploring in today's video.
But before that, some background knowledge. Calculus is originally known as infinitesimal calculus. Basically, it's part of math that examines tiny changes in a continuous function. To better understand this, you can think about how geometry is a study of shape, and algebra being the study of generalization of arithmetic operations, and calculus is just a study of tiny nudges.
The idea of calculus first came about in the 17th century. Two people, physicist Isaac Newton and mathematician Gottfried Wilhelm von Leibniz, independently developed the concept of calculus at the same time. Calculus was then gradually developed and applied to many aspects in and outside of mathematics, such as in science, where calculus is used to measure heat changes to an object, engineering, where calculus can be used to measure area and volume, and economics, such as the Black-Scholes equation used to estimate theoretical value of a financial derivative. There are two major parts of calculus, namely differentiation and integration. In this video, we will provide basic information about these two concepts so that you will have a sound understanding of this topic.
In the beginning, we understand that calculus is a mathematical study of tiny changes. But how do we mathematically understand these tiny changes? We'll start with the idea of limits. Now think about function, say, fx is equal to x plus 2. It can be easily calculated that f0.9 is equal to 2.9. Now what about f0.99, f0.999, and f0.9999? Well, the answer should be quite simple. Now to realize something, from 0.9 to 0.99, and then to 0.999 onwards, x is getting closer and closer to the value of 1, and fx is getting closer to 3. In this case, we can express this as lim x to 1 and x plus 2 is equal to 3. This indicates that as x gets closer to 1, fx gets closer to 3. Now you might think, why can't we just put f1 is equal to 3? Well, there's actually a slight difference. For limits, there's always the idea that as x approaches a certain value, but will never reach it. Do keep this in mind as later we'll be using it. We can use this concept of limits to explain what a derivative is.
Now let's talk about differentiation. Say, you have a curve y equals to fx for some function f. Loosely speaking, a derivative measures how much does impact the y value change, or dy, when a tiny nudge in the x value, or dx, is applied. Let's have an example. Draw y equals to x squared, where x is equals to 2, y is equals to 4. Let's apply a nudge in the value of x. Say it is 1. When x is equals to 3, y is equals to 9. So when x is nudged by 1 unit, y is nudged by 5 units. The nudge in the y direction is 5 times as large as the nudge in the x direction. Let's try a smaller nudge, 0.1. When x is equals to 2.1, y is equals to 4.41. This means when x is nudged by 0.1 units, y is nudged by 0.41 units. The nudge in the y direction is 4.1 times as large as the nudge in the x direction. We can create a table of dy or tiny nudge in y and dx, or tiny nudge in x and dy over dx to see how the value changes over smaller and smaller nudges in x.
As the nudges in x get smaller and smaller, dy over dx approaches closer and closer to 4. So when x is equal to 2, the tiny nudge in x will quadruple the nudge in y. If we try the same method at different x values, we'll get at x to 1, a tiny nudge in x will double the nudge in y. At x is equal to 3, a tiny nudge in x will multiply the value of y by 6. We can see a pattern here. A tiny nudge in the value of x will correspond to a nudge by a factor of 2x in the y-axis. Or to put it more rigorously, dy or the rate of change of y over dx, or the rate of change of x is equal to 2x.
We get this through some pattern spotting. But what about more complex expressions, where the patterns might not be so obvious? Recall that we want to find the ratio of dy over dx. As dx gets smaller and smaller, we can put this as the limit of nudge in y over nudge in x. As the nudge in x approaches 0, Notice that the notch in x approaching 0 here does not mean that the notch is 0, which would make calculations impossible since we can't divide by 0. Instead, it is saying what will happen if the notch is nearing 0 but never reach 0. If we replace notch in x as a variable h, we can represent the new value of y as fx plus h, which means the notch will be fx plus h minus fx. As a result, we have attained the rigorous definition of derivatives. We can apply this definition to our x squared formula and get dy over dx equals to 2x as well. One real-life application of derivatives is to find velocity. Velocity can be described as change in displacement over change in time, or v is equals to ds over dt, where v represents velocity, s represents distance, and t represents time. For example, if a train takes 3 minutes to travel from station A to station B, which is 3.6 kilometers apart, this will mean that the average speed of this train is 1.2 kilometers per minute, or 72 kilometers per hour. An issue with this is that the train's velocity might not always be constant. Therefore, to find the instantaneous velocity of the train would be problematic because at a specific point of time, there's no change in time, or dt is equal to 0. Bringing this back to our formula, v is equal to ds over dt. It is impossible to find velocity v, since we cannot divide by 0. We will get a value infinitely large, which is not really the case. Therefore, instead of tracing the instantaneous speed at fixed time, we do a little bit of trickery by measuring the distance this train passes, or ds, at a very small interval of time, or dt. Now, we can get the velocity as time is no longer 0. As v equals to ds over dt, the smaller the time interval, the closer it gets to the instantaneous speed at an exact time interval, but we can actually never make dt is equals to 0.
From here, we can build our way through the rest of the derivatives-related problems. There are a slew of potential results that I will link in the description that will explain more about derivation of more complex functions, such as square roots, fractions, and more. Derivatives also have some interesting properties as well. For example, when you add or subtract multiple terms of the same variable and want to make its derivative, you can take the derivative of each term and add or subtract them together. The derivative of products or ratios of two terms is slightly more challenging, and I'll leave you a link down below if you're interested. For better understanding, fx is equal to x squared and dy over dx is equal to 2x are plotted graphically on a plane as shown below.
For better understanding of calculus, I highly recommend you watch the video series made by Tak Lu and Bryan, where he covers in depth each important area of differentiation, as well as integration. That is all for this week, where we talk about differentiation, what it is, how to do it, and what are its applications. Tune in next week, where we'll explore more in depth about a major branch of calculus, integration. Don't forget to hit like and subscribe on your way out, and we'll see you soon.